So we are going to see how we just in the previous discussion we had the representation of communication rules and I could say operators, eigenfunctions, and eigenvalues. And in today's class, we are going to see how we can have identification of operator matrices. So the identification of operators and matrices can be complete and the definitions may be overlap or not necessarily marked exactly. So if we have to have a nuance of how we can geometrically interpret operators, who suggest that suggesting that linear operators can be replaced by matrix operations in the process of finding eigenvalues or eigenvectors. So, draw. But the point is, we can have the continuous cases as well as discrete cases. In the discrete cases, the mapping is obvious, but in continuous cases, there are some subtleties. So, for example, if we have components, we call matrix P, I, J, and the components are defined by the application of operators, U operator, and so operating on this with the unit vector I. Then T, I, J, or T, K, I is it's acting on the U operator acting on the unit vector epsilon I. So we can write Ki as U operator epsilon I. K subsequently. So if we now apply for the discrete cases, the discrete cases, this is equal to the summation in the sense that U operator acting on chi, basically I, summation, so it's how to apply for discrete. So you can have this I and this summation in the chi. U operator acting on so chi I, this I and I, we will use this summation with chi I. So U operator acting on chi. The left hand side is here component of the function, here component of the function, where U operator acts on this chi. And you can also show the permutation character of this operation side. P of Ki is equal to P star Ip. So you can have these Rki and Ip and just this is called exchange once you have permutation. So if you write 8 of section 15 and 18 of section 10, so you can have 8 of section 14. You can have, if you want to have, so from previous equations, 8 of the 14, 8 of the 14, 8 of the 14, the previous, if you remember, previous 8 of the 14, 8 of the 14. We know that U operator phi of chi is phi of U operator chi. So you can see from this property, this operator operating on file. You can, these are the exchange, exchange this, you can flip the properties. And using the same property out here, means u of y operator acting on phi plus then value minus this is equal to 0. Phi of u operator acting on phi. So it follows from this. So it's equal to k times u operator phi now phi u operator phi. Now you are coming to this property u operator phi acting on chi k diagram minus no phi is outside phi u operator acting on chi I is here. So you can see if you have, for example, if you want to just have two subscripts or solutions of two indices, ki and ki, then so you can write it in terms of you can write it as u operator acting on this in terms of this TKI or chi-ITX. You can have two indices, you can have two indices here, operator acting on chi, operator acting on chi with this xi TKI. You can write it as TKI, phi I, x t star minus, you can write it as Pki star, Pi star, phi I chi k star. So you can see u operator here and u operator here, which is acting on chi star, and u operator here. And you operator here acting on chi. You can have this identification here and here, and you can have two symbols. You can get phi I chi k star outside. So this means TKI minus T star I. Phi the summation k and I. So we therefore have, so from what is 0, you can have from this also, you can have TKI is equal to PI k star. So we have arrived at the same property here as well as here. In the first case, we have used the simple equation. In the second case, we have used this property and written here operator acting on this phi in terms of this phi TI, and we can arrive at the same property. So really, in the case of this is the discrete case, always coordinate, you can always coordinate operating matrix to a linear operator. So which may not necessarily, may not be always the case for continuous case. So we have to use the summation in the discrete case where we can always coordinate an operating matrix. We can always coordinate a matrix operated with linear operator. We can always coordinate a matrix operated with linear operator. Now we are going to the continuous case. The continuous case, the application is u operator chi 2 prime is chi 2 tau of 2 prime. So the left hand side means that the value of a resulting function is q prime. And the Hermitian character of the operator can be defined as 2 prime is equal to tau star 2 prime. For a continuous case, you can use so in the discrete cases, the value has some discrete value, eigenfunction, eigenintegral. But for the continuous cases, you have the integral. You can have continuous integral out here, which can take any value. So the property of this Hermitian property can be like this. So Q, it might be 2 prime. Yes. Q 2 prime. It's like this. Now it's 1. 2 prime, 2 tau star, so 2, it will become this, this. So, kind of condition can you change, we flip this to this, and this to left. Or, we flip this to this, and this to this. Sorry, it may flip this to this and this to this. So 8 and 14, the fact that 8 and the 14 is 8 to 14, that 8 to 14 can be applied to property. Can be applied to with no operator matrices. So this equation can be applied if there are no operator matrices. This is no operator matrices exists. And for the operators of heterogeneous type, the one is the homogeneous case. In the heterogeneous case, the operator, the hermeticity conditions, condition for operators in case of heterogeneous functions, not in case of homogeneous functions. It is usually equal to the substantiate or its thing, its problem. So in case if the continuous operator not operator matrix does not exist, we take recourse to our understanding of Dirac functions. It turns out that our definition of two coordinate and this derivative require a treatment for matrix functions. We will require a treatment in course to this function. So if you remember, and the matrix function operator, and if you remember in the previous class, we had position and momentum of coordinates defined like this. For this, for f of q, it was mu f of qi. For pi square, we have x square, we have 2 pi square, d2 by d2 square. Remember? Now we can have starting from the cluster function. So if we, yes, so the question is, once you take recourse to operator method and operator function, it has one advantage against, or it has an alternative way of other than going arriving at these solutions apart from Schrödinger's differential equation. This is another alternative way of arriving at solutions or eigenfunctions or eigenvalues of the entities. So in the sense that if we can formalize it in terms of some definition of matrices, then we can say we can say that we can say that um, we can see it in terms of matrix postulate, where we can construct a unity matrix. We consider a unity matrix phi which transforms DIP into a diagonal matrix, such that DIP into a diagonal matrix, such that UI into delta IQ. So the matrix whose value is shifted from 0 for I is equal to K. So equally this how we can construct the matrix postulate. The important thing what you see is that the advantage which this matrix method has so historically Heisenberg, Bohr, Leibniz, Dirac had independently the matrix method has been introduced by Heisenberg, Bohr, and Schrödinger, independently of this Schrödinger and de Broglie. They arrived at it by real mechanics. The point is of showing the equivalence between the two. That mathematical, the ability of Schrödinger were solving this problem through differential equation as compared to unity matrix phi I is that it's possible where we have shown this differential equation. And equivalence between operator and matrix. So matrix form is basically replaced by this thing called operator form where equivalence between matrix and operator mechanism is not used. So the use of Schrödinger's equations makes matrix mechanics not necessary. Now the important point is that how we can determine probability distributions. So it's very important to just have this functional context of trying to visualize the relationship between actual observables and the theoretical or mathematical constructs, and the functional relationship between the two things. How can relate eigenvalues, eigenoperators, eigenfunctions, which with the measurements, which may be rare with the observables. In one case, or in case of Schrödinger, of the differential equation is related to the observables we are introducing. So here, since we have taken the course to probabilities as compared to having well-defined numbers, so we can have those class of probabilities which are defined both for those discrete as well as continuous representations. Where those eigenvalues or eigenfunctions which are eigenvalues which are constructed from operators acting on those functions which will do those eigenvalues are supposed to exist. So in principle, the eigenfunctions may not necessarily have the functional relationship between observables and the thing. The idea of eigenfunctions is more you can have its identity as a mathematical functions. Also, not necessarily relating with relating them with some observables. So if you want to now, if you don't couple those values also further with the probability distributions which are associated with that. So we have to define those probabilities and these functionalities both discrete as well as continuous representation. Here eigenvalues and eigenfunctions are normally they are usually indicate what I would say as probability distribution. And probability distribution means they might have some range of values. So a general statement which can be a general statement so a general statement which can be is general pattern where the side can be quadratically integrally normalized. Then we can have side 2 square is equal to 1. So before we define observables, we must first state what can be the possible values. There can be three set of rules. We must specify. Rule one says that eigenvalues constitute the possible values of the entity within a given context. So eigenvalues constitute the possible values of entity in the new context. The context may be, for example, the Bohr's particular view of a defined probability. For example, and rule, for example, so this is rule one, so is rule who states that so rule two states which is also called spectral decompositions. So rule two says that you have to expand, which is spectral decomposition. Here we can expand the psi of 2 into eigenfunctions of the considered entity. Psi have the squares of functions sigma I or sigma u, then determine an eigenvalue ui or ui to be infinite. So there can be two cases for it. One is the discrete case, where the psi of q is equal to sigma I by and probability is given by S of u is sigma square. And for the continuous case, you can have psi of u, you can have, so in the discrete case, psi of u is sigma of phi of u. And for the continuous case, you can have the rule of integral consideration. Here, this is equal to sigma u phi of u to a. So the probability of S of u is sigma of u square, where this P signifies the probability consideration. Now we can sometimes use, since this book has used D, so for the probability, the symbol chooses D rather than P. So D of ui is sigma I square, or D of u is equal to sigma of u square. So now, because of 1, 3 and 9, one is basically this equation, that probability of this for continuous psi of q square and dq is 1. So we can have sigma of I square is 1, and sigma of u is d is 1. So if phi I are n eigenfunctions don't give eigenvalues, then sigma of I has to be 1 again, sigma of phi of I into 2, where sigma I square is equal to 1. So this is I is equal to 1 again. So this is rule 2. And the rule 3 is this is 2, this is 1, and if you write root here, you say that probability value of value of 2 or set of values of 2, 1, 2, 2, 2, and which are in the order is like this P of S of 2 is psi 2 square. So the rule also makes an attempt to see things in terms of normalization. Where we normally say that probability at n comes out to be 1. This rule 1 and rule 3 can be abstract mathematical for observational entities. For example, this sigma I is basically here we have also psi I is so sigma I phi I. For discrete cases. So sigma is basically what? Sigma is basically sigma is basically so sigma is what sigma is. You can have how operators act on the thing and give you some exact values. And this is the idea of normalization, how we normalize the things. So we can say these postulates connected with the observational aspects of the quantum mechanics or probability predictions, which are expressed as the square of the complex wave functions. And the second one is the case of how we can define continuous probability distributions for the case for continuous case, in which we have used the integrals. So here the problem becomes how we can signify the observation problem becomes how we signify the continuity. Because in the real life case, the problem historically when it was seen that both continuous cases as well as discrete cases, the eigenvalues and eigenfunctions, eigenfunctions operated on by operators which give particular eigenvalues, which can be discrete as well as continuous. The discrete cases mean those stationary states of the discrete cases means the transition probability, which had discrete values when there is transition from state A to state B. And the continuous eigenvalues where that when the electron moves to continuously move around and the circular fashion. Now the question is we do a small exercise to show that how we can write these discrete as well as continuous cases more particularly continuous case in an integral form, which will have some sort of similarity with the way which will ultimately give us how we can write expectation values. At the end, we are considering expectation values of given observable, which we construe after measurement, and that observable is constructed out of those eigenfunctions operated upon by operators which use eigenvalues, which may lie in those which might have a continuous parameterization or discrete parameterization in terms of probability distributions. So the complex conjugation can write as, for example, you write du is written as sigma of u square, and psi is basically sigma u phi of u to du. So A u can be written as First, you are going to use as for it's du, and this means you can write it as this du has a similar structure. So you can write it as integral of sigma u square du. So you can have complex combination with sigma u, sigma square du. So you can have this integration sigma u. You can have sigma u psi star u phi of u du. So we have basically sigma u. So we can write psi u as like this. Psi u like this. So we can write it as psi u as this side. That's side. And for psi u sigma u it's 1, and again sigma star u it's another thing. So you can write it twice, so you can write it like this as a double of this. Now we can see it. We can see it in terms of linearity of operator. U operator acting on side 2. U operator acting on the side 2 will give U operator sigma u phi of u2 du. It means you can have U operator on this. You can take it inside and get U operator acting on sigma u phi of u to du. Or you can have sigma u operator phi acting on u of u to du is equal to sigma u phi u to du. So 5 goes this 5 to so now we use the last operation for 6 and 14. So we have used this property. U operator phi of u is equal to U of phi of u. U operator acting on phi of u, so we can write it like this. Side that at the end, can write A of u, A of b, this one, as psi star u operator psi of u du. Where psi of u can be written as like this. So we can replace u by u operator, and A is the average or the expectation value, which is given with psi u operator. This is psi of u. And psi of u can be represented as psi of u is represented as like this. So psi of u we will have to write it in terms of this symbol for this continuous radiation. Psi of u is this, and psi star u can have this complex combination. So you can have this as the expectation value. operator is inside. So you can have the probability average value for the probability distribution for the final set of eigenvalues, which may lie in that range. So we have given both probability distribution, which is basically how we can have eigenvalues or eigenrepresentations in certain set of continuous as well as discrete values in that. This is how we can represent it. So I can stop.